So, welcome to the lecture on stability and steady state error. So, in this lecture, we will discuss about Routh-Hurwitz criterion for stability. So, in the previous lecture, we saw that we can tell about the stability depending on the location of poles. So, we need to solve the denominator of the closed loop transfer function to find the values of the poles, and then we can locate the poles on the S plane to know whether these poles are to the left side or right side of the plane, and then we can tell about the stability. Only the information about the location of poles, whether they are in the left side or right side, is important to tell about the stability, not the exact values of the poles. So, therefore, we know we do not need to solve the equations, characteristic equations for the poles, but only we can know that how many poles are to the left side and how many are to the right side, or how many are on the j omega axis. We can know about the stability, and we will use the method given by Routh-Hurwitz criterion for stability. So, this method yields stability information without the need to solve for the poles. As using this method, we can tell how many closed loop system poles are in the left half plane, in the right half plane, and on the j omega axis. So, to find this information, we need to generate and interpret the Routh table. So, we will develop the Routh table and we will discuss with some examples how to find the stability information. So, let us take that we generate the Routh table . So, let us we have this system . So, this is equivalent closed loop transfer function, equivalent closed loop transfer function. This we have already defined and discussed in the previous lecture, that how we can obtain the equivalent closed loop transfer function of a given system. So, this is our this denominator will tell about the information of the poles and their locations. So, we do not need to solve this equation a4s4 plus a cube s cube plus a2s square plus a1s plus a0 equal to 0. So, we do not need to solve to find the values of s, but we can create the Routh table. So, initial layout, so what we will do, so to create the Routh table, we begin by labeling the rows with powers of s from the highest power of the denominator to s0, and start with the coefficient of the highest power of s in the denominator and list horizontally in the first row every other coefficient. Then in the second row, we list horizontally starting with the next highest power of s every coefficient that was skipped in the first row. So, we begin by labeling the rows with powers of s from the highest power of the denominator to s0. So, we have highest power here is s power 4, and the coefficient of S4 is A4. Then we skip one, we go to A2, then we skip, we go to A0. So, we label like this these coefficients. So, we start with the coefficient of the highest power of S in the denominator and list horizontally in the first row every other coefficient. So, here every other coefficient from A4, then A2, then A0. Then we start with the second highest power, that is S cube, and S cube's coefficient A3, and then every other coefficient. So, A1, and then here is nothing, so we put 0 here. So, now other term S2, S1, S0, this we have to find this table, these terms of this table. So, here we can see that to find S2, so let's here S4, A4, A2, A0, then S cube, A3, A1 and 0. Now S2, S square. So, this to get this term we will take minus and determinant, and the first column will be the coming from the top first two rows, the first column element, that is A4, A3, and the second column will be the elements to the next column, that is A2, A1, and this will be divided by this element here A3. So, each entry is a negative determinant of entries in the previous two rows divided by the entry in the first column directly above the calculated row. So, here this column and the next this column by this element A3, and let us say this is B1. Now, for this second element we will have minus, this will be fixed A4, A3, this first column will be fixed in this row, and then this element will be the element to the next column of this column. So, A0, 0 upon A3. So, we see that this column is fixed and this first element will only come to the will divide these elements of this row, and let us say this is B2. Then this third element minus A4, A3, then here the next one, if nothing we assume 0, 0 by A3, and that is equal to B3, and this is 0. So, we have got the next row of this table. Now, the S1, now we will get again apply the same rule and we will get minus. Now, the next the previous two rows column is A3, B1, A3, B1, and the next one is A1, B2 divided by B1, and let us say this is C1 equal to C1. Now this element is minus A3B1. Then next element, so here we have 0 0 by B1, and that is equal to C2, and that is equal to 0. Then this one minus A3 B1 and then 0 0 by B1, that is equal to C3 equal to 0. Then come to S0, so minus here this column B1 C1, and then the next column B2 and 0 by C1, and let us say this is D1. Then minus B1 C1, and then the next column 0 0 by C1, that is equal to D2 equal to 0, and this also minus B1 C1 0 0 by C2 C1 equal to D3 equal to 0. So thus we have created this is called Routh table. So we have created Routh table for this closed loop transfer function. So you can see here A4, A2, A0, this second row, this is third row, and here is the fourth row, and this is the fifth row. And similarly here is this column, first column, then second column and third column. Now from this table, how we will know that how many poles are to the left side or how many poles are to the right side. So suppose this is our S-plane. So we have to watch on the first column. So first column elements, so A3, B1, C1 and D1. These are the first column element. So we have to notice that whether these elements are changing their sign or not. If there is one sign change, means one pole is to the right half plane. If there is two sign changes, then two poles are to the right half plane. So suppose here so also A4 here A4, A3, B1, C1, D1. Suppose here A4, A3 are plus positive, but B1 is negative, then one pole is to the, and then again this is positive, means two poles either this way or this, it could be to the right half plane. And so even one sign change will tell that one pole is to the right half plane, and so the system is unstable. So the table is complete when all of the rows are completed down to S0. Now the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. So number of roots or poles in the right plane is equal to number of sign changes in the first column, and a system is stable if there are no sign changes in the first column of the Routh table. So if there is no sign changes in this first column, then the system is stable. So let's take one example. So we have this equivalent closed loop transfer function. Now we have to generate this Routh table. So highest power is s cube and the coefficient is 1. Then the we skip this 31 and then we have 0. Then s square we have 10. Then we have 1 0 3 0 and then 0. Now we generate for S1. Now in this one row we can cancel out this. If there is some common element we can take it out. So we can, there is 0. So 1 and 103 we can write. Now we create this table. So this element minus this column 1 1 and then the next one 3 103 by 1 and this is equal to, sorry, this is 31, we have 31 this, and so we will get minus 72 this element. Now the second element minus 1 1 and 0 0 by 1, that is equal to 0, and the third element will also we will get 0 because this column will be 0. Now come to S0. So again minus, here is 1, this is minus 72 and then the next one 103 and then 0 by minus 72 equal to 103. Now this one minus 1 minus 72 and 0 0 by minus 72, that is equal to 0 and this is also 0. So we can notice here that we have two sign changes. Here it is plus plus, but here it is minus. So there is one sign change here, then again it is plus. So second sign change here. So there are two sign changes, and two sign changes means we have two poles to the right half plane. So when we plot this pole, we will find that this is sigma j omega. So two poles are here to the either this way or this way, whatever is applicable. We don't know this information, but we know that the two poles are to the right half plane, and because this is power 3, so one pole is to the left half plane. So because two poles are to the right half plane, the system is unstable. So we saw that how we can, using the Routh table, we can generate Routh table for a system by finding the equivalent closed loop transfer function without calculating the position of poles, or without solving for poles. We can tell about the stability or instability of the system. So, now we considered some special cases. So, there could be special cases because here we are using the first column terms as the for division in the subsequent rows, and suppose these terms are 0, A3 is 0 or we get B1 and B1 is 0, then how we will proceed, how we will be able to make the Routh table. So, there are some special cases, and so if 0 is only in the first column, so if we find 0 in the first column somewhere, it will be difficult to compute for the next rows. So, how should we deal with this kind of cases? So, we will discuss some special cases. When 0 only in the first column. So, here we assume that 0 is only in the first column and not all complete row is 0, only at least one element is non-zero in the row and first column element is 0. So, when this happens, so let us take this example like T is equal to 10 upon s power 5 plus 2 s 4 plus 3 s cube plus 6 s square 5s plus 3. So, we have this is our transfer function, equivalent transfer function. Now, let us try make the Routh table. So, s power 5 we have 1, then next one is 3. So, 1 then 3 then 5, 1 3 5, then s power 4 2 6 and 3, then s power 3. So, we will take minus this column 1 2, then the next column 3 6 by 2. So, when we compute this, we will get 6 minus 6 equal to 0. And this one minus 1 2 5 3 by 2 equal to 3 minus 10 minus 7 by 2, and this one will be 0 because this column is 0. So, this will be 0. So, here we got 0. Now, if we want to compute this term S2, so this 0 will come to in the denominator and we will not be able to make this row because that is undefined. So, there is one method that we replace 0 with epsilon, where epsilon is some very small quantity we assign here in place of 0, and we carry on the making this row, making this table, and then in the last we approach this epsilon as plus 0 or minus 0, and we will see whether what is the sign change. So, let us give this as epsilon, and now we calculate this table. So, this is minus, we have 2 and epsilon, and then this 6 and minus 7 by 2 by epsilon. So we will get, so minus 14 by 2 minus 6 epsilon, sorry, minus 7 minus 6 epsilon. So this is 3 minus 10 minus 7. So this is plus. So here is plus. So 7 minus 6 epsilon. So this is minus. So 6 epsilon minus 7 by epsilon. And this one is minus 2 epsilon and then 30 by epsilon, that is equal to 0 minus 3 epsilon by epsilon. So this is 3 and this is 0. Then we compute S1. So when we compute S1, that is equal to minus epsilon and 6 epsilon minus 7 by epsilon, and then that is 7 by 2 and 3 by 6 epsilon minus 7 by epsilon. And so this, we solve this, we will get 42 epsilon minus 49 minus 6 epsilon square by 12 epsilon minus 14, and the other terms will be 0 when we compute 0. Then the S0 will be here 3, 0 and 0. So now let's take the sign change. So here epsilon is, let's say that it is approaching to 0 from positive. So this will be, this is plus, this one is plus, 2 is plus. Here if epsilon is positive, it is plus, of course a small quantity, and this is positive, and so this is minus 7, so this is minus negative, and here this is positive, they will be positive, so here minus and here is minus, so it is positive. So minus 49 by minus 14, that is positive, and this is positive. So we see that here there is one sign change here and then other sign change, two sign changes. Now let's consider epsilon as negative. So this is positive, positive, then here it is negative, then here negative minus negative by negative, so it is positive, and again the negative, so it is negative, and this is negative, so this is positive and this is positive. So again here we have two sign changes, one here, other is here. So here out of 5 poles we have 2 poles to the right half plane and rest 3 poles are here in the left half plane. So because 2 poles are in the right half plane, the system is unstable. So I would like to stop here, and we continue in the next lecture. Thank you.